Hello and welcome. In this video I want to show you how you can create a robot code that you can send to the robot in order to assemble parts or drive along a curve and all sorts of different robot programming from Rhino and Grasshopper. So as you see here in the Rhino file, there's already a simulation of the robot. In our case it's the UR10, and it already has a gripper attached to its wrist. So as a first thing, what I want to show you is how you can move the robot to a certain position. In our case it's not points that give the direction for the robot, but these planes here. As you see here, there's a circle, and in the circle you see the plane, and the robot will always attempt to find a solution to go to this plane here. As you might have noticed, the robot mimics a human arm, which is basically based on the joints. It has the similar amount of joints as a human arm has. And yeah, what the program we are using here does is it solves the inverse kinematic. So the way from how we get from this point over here with all the predefined joint positions. So you can imagine, in order to get to this point with a tool center point, we have to calculate each angle of each joint, considering the length of this arm, for instance. So all of that is done here in this creat program, and what the software we're using is robots. I want to quickly show you how you can install it if you haven't done already. So one thing you have to do is you have to go to your folders, specifically to your documents folder, and here you have to place the folder robots. You have to create a folder called robots in the documents, in which you place all the robot files. This is needed so Grasshopper can get the geometry and the joint measurements from these files. So there's, on the one hand, there are different 3D files, the Rhino files, which they contain the meshes of the robots, and as you see, there are several different robots. I don't know if you can see it if I go to large icons. There's a Beakley robot, there's the robot setup from Sita, Bartlett, and so on. And moreover, there's also a XML file that contains the robot's dimension and the joints, the joint names, which are also needed for our robot plugin to work. And then I already have it open here. It's robots. Robots. You will see it up here. If you have this file accessible to you, you can easily come to this to the commands here by just go, for instance, on the program and hold Control Alt, and it will, and press on this component, and it will direct you here. But besides, you also have to install the components, and therefore you have to install the DLL and the Grasshopper component file into the Grasshopper library folder. Yeah, so this is the DLL file, and this is the Grasshopper component file. Please make sure that you right-click on them and make sure that they are not read-only or hidden, yeah, on all of the files. Same goes for the for your robots files. Yeah, you might even have to make sure that the folder is not read-only. Yeah, as you see in my case. Just make that sure. Okay, and after that you might have to restart Grasshopper in order to access that. The main features or the main components that are needed for from robots to create robotic code is, on the one hand, you have to load the robot system in our case. And as you can see here, we can switch between different robot systems. Here in DDU we also had we have two different URs, but we also had once a setup where we had a ABB IRB 120 here. So you can switch between those robots, and you can even replace the base, which is basically this position here. You could change that by an input plane, which I wouldn't really recommend it. I highly recommend to leave the robot at the 0, 0 plane, which is the standard here, the world XY, to leave it like that. And then from that you have to create a program, and the create program component needs, besides the robot system, it also needs, you can give it a name, pick and place for instance, but it also, something really crucial is the targets as a list. And targets you have to define. And how do you define targets? So here are a few different setups. So the first one is, for instance, with this input curve. Yeah, you don't input curves or points or lines or anything. You have to input planes. But I derive from this curve. I check if it's planar, and so I get the plane of the, in my case, circle. If I would directly give that into the target, which you see here, it will flip. But basically we have to define targets, yeah? So therefore you go here in components and create a target. And the target, first thing it asks for is a plane, a target plane, and then there are several more commands like the robot configuration. And if I press on that, we can see here, up here I define some more properties, like which solution it should choose, which kind of movement, which speed, and which zone parameter. The wrist was relatively clear. You see that, how it changes. Linear, you can imagine, instead of, there are two ways for the robot to solve how it reaches a point. But for most of our cases, the linear setup is will be all right. Then there's the speed parameter, which is millimeters per second. Again, here I would recommend to keep that relatively low in the beginning until you make sure that all the targets can be approached and there are no problems in the program. And then there's the zoning parameter, which will be more important when we have more targets, because the zoning parameter will ignore planes that are within a certain range of the previous target, but more for that later. So you see here at the moment the robot does a really weird movement because I want to approach this plane here from top. That's why I have to flip the plane. If you don't have that component, I'm quite sure it's within the Fox plugin for Grasshopper. You might have to download that if that doesn't show up. So what I've done here is I created a target with all these parameters and based on this plane. So now I can just move the robot in all positions, and I can also change the orientation of it, because it's based on a plane. If I would give in the XY plane here, like transform the initial plane, now you see, there's the XY plane. Okay, now it's flipping again, so it's flipped again. So probably it makes more sense to hand it in here. And now you see the robot, no matter how I rotate it, will always stay along the XY plane, which we don't want that for now, but you could do something like that. Yeah? So that's how you define the robot. So you can really easily imagine now, I could also give in more planes. So let's try that. If I have two of these curves, I give in two curves, set multiple curves, And now you see this plane doesn't affect the robot anymore, only the first one. So that's where the simulation comes in. Because at the moment I'm on the, you see here we can move in the simulation, we just have to hand in our program, which we defined over here, the program, and we connect it over here, and then it asks us for the time, which is a slider from 0 to 1, and then we can see how the robot will most certainly move. There's no guarantee that the robots tool developed by Vicente Soler from Bartlett works 100% perfect, so there might be small errors, but most certainly this is how the robot will move. Yeah. And as you see, you can also normalize it from 0 to 1 or not normalize it, so then it will be the time that the program takes, which at the moment is 2.1 seconds. Yeah? And if I zoom out now out of my program, here are also some analysis tools. As I said, there's the duration of the program, there's the actual program that will be sent to the UR controller. There are some more informations like the robot stand, the workspace, both as a curve but also as a circle. So you know already when you're placing something out of the reachable area of the robot. You can have a collision detection, which I would, for most of the times, I would not recommend to do that, but it might be worth checking it, or it's good to know that it's there in order to test your program. There's also analysis of the joint movements, which I don't want to explain in more depth now, but basically it says how much the joint moves. Yeah, for instance, at the beginning all joints move a little bit, and then those move way less than this, for instance. We see that there are warnings. So at the moment, first target and robot change to joint motion using axis rotation. This is due to the fact that the first target always has to be approached by the controller in joint space or by joint motion. We later on change that to linear motion. There's also one targets are set to linear with a forced configuration, the first one being target 1 in robot 0. So you see there are some more informations, and then there's the upload button. So we can upload it to 2 different robots, and we just have to connect to the right robot and upload it. And we can even play pause, which it is not, sometimes it creates some problems. Yeah, nevertheless, so that's basically how you would define different goal positions. But you can also, instead of just handing it every curve, you can also give in a curve as a guiding, yeah, as I did here, for instance. Here you see all the planes are aligned perpendicular to the curve, and if I give in this here into the target of the robot, you see now the robot moved over here. And now if I go through the simulation, you see how the robot moves along the curve. But you might also have noticed there's a weird movement happening here on the wrist joint, which you might want to avoid. In this case, it might be worth to check if there are better solutions there for the robot. And you see here now the robot moves way smoother along the curve. Yeah? Although at this very moment the movement is quite rapid. Yeah? So if we go at the analysis, you will see, yeah, there's weird movement happening over here. So that's those two approaches. Yeah. So you can generate a curve, which is the guiding curve for the robot, or the one planar idea here to create targets. And then there's a way more complex approach in which we also can define gripper commands, yeah? As you see here, for instance. Because when you go to the target components, you not only see this zoning and speed parameters and everything, which, by the way, you can turn off if you right-click onto the component, and you can switch on and off all this different inputs for the command. But you can also create robot commands, which can contain informations like wait at a specific moment for 1 second, or set a digital output, or an analog output in our case, to open or close, for instance, a gripper, which is done or communicated to the robot via digital or analog outputs. Yeah? So the robot program automatically sets the analog output 0 in this case to the value 0.01. You will also see the target is asking you for a tool, and that's what we do up here. We create a tool definition, which in our case, you see here, is for once the closed gripper. That's a mesh. We have to join it to create one mesh out of it. And then we define this tool, which it's the gripper. We could even call it gripper open. And we can define a weight for it. In our case, that's only 0.8 gram. And thereby we define the tool, which is called gripper open. And we hand it over to the target. And yeah, so that we do that for open gripper, but we also have to define the closed gripper, which you have to define as a mesh. So that's pure geometry. That doesn't have any reactive tools. So if we want to see how they change in between, we have to create different targets. So before you saw we only used one target component, but in this one here we use several targets. Let me show you how this program looks. So it comes out from here. Go to the simulation. You see it's a pick and place command that goes from left to right and all the way to the top. Yeah, so there are a lot of there are way more commands than what I showed you earlier. But again, it's all based on planes. Yeah, you see here, these are the planes. And what we do here is we move the planes a little bit. So we have an approach plane, and we have a plane where the robot grasps something. And at this position, for instance, whenever he comes here, he has to close the gripper, whereas at this position the gripper is already open and it just approaches it. And then we have to take those two targets and weave them together. Yeah, so one after the other, we weave them together. And then in our case, we also need a pickup location, which is this one here. And we want to use this pickup location, and we do kind of the same. So again, we have an approach plane, which is like a few centimeters higher, and a pickup plane. And then again, we weave them together. And then we have to figure out a way to weave those two together, which we do over here. And then we can hand that over to the robot. In order to generate the plane, we had these two approaches here, which this is a little bit too complicated. Maybe I show that only to the one who are interested. But more easily we define our geometry here, and we take one input curve, which is this one, at which we have all these elements which are based on this plane. So what we can do is, you see, these are, or here are our target, this is our goal, but this is our pickup location, so that we want to give in here. So we can just connect this one over here. So now we have this as an input curve, and this is our target. We can place the target over here. And now the robot will go from move from there over there. As you may notice, the modules don't change as they are not part of the simulation yet. If you wanted to do that, you could easily you have to figure out a way how you can put the module at the right place in a tool. So you have to place it in this tool, and then the robot would also carry, because it becomes part of the tool, would carry an object. So again, these two groups here, they take care of the placement and the pickup. So in a way, maybe it's easier to understand if we move them around. And this is basically your one is your stack, and one is your goal geometry, which you need. Okay. And here we have yeah, no, I don't want to go into that now. I hope you understand everything. If you don't, please just ask me, write me a message, comments or anything on Moodle or here underneath the YouTube, and then I will clarify things that haven't become very clear. Thank you and see you soon.